I normally wear an academic hat, but the organizers asked me to wear an industrial hat for this presentation. I searched my closet last night with my wife and failed to find it, but I'll do my best. So you can imagine that I'm wearing a hat that says TTI on top. And TTI actually stands for Terra Technologies Incorporated, who are the people that are putting this technology that we developed into practice in several countries around the world. So motherhood and apple pie is always a good way to start a meal. Would you like to help decarbonize energy systems? Would you like to help recycle energy that is inherent in biosolids? Would you like to sequester carbon permanently in a form that cannot possibly be released back to the atmosphere? In other words, solid. Would you like to reduce your sewage treatment costs? Would you like to reduce the environmental risks of sludge spreading? We have to say that 5 times very quickly. Sludge spreading on fields and in areas where there is less concern. And I do point out that the city of New York, if I'm not mistaken, sends about 40 tanker cars every day of treated sewage sludge to West Virginia to spread it on non-agricultural land. New York to West Virginia. Okay. Well, here's the world's first biosolids injection site based upon a patent or two that I helped write. In Los Angeles, this project has been continuing on just a very trial basis for a number of years with great objection by every civil engineer who does waste management and feels that his or her job might be threatened by this new technology. So it has gone over a lot of bumps, but the experiment, full-scale experiment, is still going on. What happens? Well, biosolids after, say, secondary treatment is slurried with wastewater. Okay, so you have waste and waste, and injected at depth in a suitable environment that has porosity and adequate permeability. So it has to be in a sedimentary basin environment. And at depth, all of these sediments have populations of anaerobic bacteria that exist in the form of spores. And when you send them food, they come back to life and start eating the food. To them, biosolids is food. So they turn the biosolids into carbon dioxide, water, methane, and a compound that you might consider to be coal or something like that. It's a carbon-rich residue that is a solid and insoluble material. It's like coal. This is actually the process of coalification, is what they say. So it's elemental carbon largely that is permanently sequestered. And the environmental risks are extremely small because you're doing this well below any potable water, hundreds and hundreds of meters below potable water. Now, approximately, if you have pure carbohydrates, not just carbohydrates, but pure organic matter, about 15–16% of the mass of that organic matter through this process will turn into methane. That methane is recoverable. And I'm sure you really want to know this, but your own personal biosolids wastes generate over 600 kilograms per person per year of carbon dioxide equivalent. Okay? So if a large portion of that is being sequestered permanently, and there's energy recovery, you're eliminating the impact, your own personal impacts. And maybe of particular value for countries that do not have highly sophisticated waste treatment facilities, as we do in North America. So India is my example of that. We'll come back to India a little bit later. Large population, etc. So a slurry of biosolids is injected by a process of continuous fracturing, which is not dangerous because the strata are permeable. And filtration of solids happens, and the water dissipates into the deep environment at depth where the porosity is very, very substantial. And then decomposition starts. Depending upon the temperature and the composition of the biosolids, the decomposition will be essentially 95% complete within 18 months to 5 years. That's because of different temperatures in different locations and matters like that. And at that point, the methane can be recovered. So what you see here is a well bore, and the injection is taking place through the perforations at the bottom of the well bore on the right-hand side. And there's a number of security barriers above the injection site that keep any efflux from happening and also trap the gases that are generated down below. This idea evolved from deep injection of granular wastes in the oil industry. This is one of the first ones that this company built, and I did some of the engineering on this project back 21 years ago, where all that waste sand in the background that you see, piles and piles of it, was injected successfully at a depth of about 500 meters over a period of many months, and it was co-injected with wastewater that would have had to have been treated in any case. So it's getting rid of two waste streams. This facility, which is active in the Duri oil field in Indonesia, has turned the Duri oil field from an environmental disaster to an oil field that is almost at zero waste discharge at the surface for liquids and solids. Oily fluids, produced water, waste sand, tank bottoms, tank sludges, many of them rich in carbon, are injected in a series of wells at a depth of about 500-600 meters far below groundwater, and also in an area where there's a lot of rainfall so that there is no possibility of the efflux at the surface. So this is now a zero discharge injection facility. The biosolids concept is essentially the same, only we're putting in a very biosolids-rich slurry that then is later exploited for the methane, as you see here from that horizontal well at the top of the zone. Well, this is the permit that was issued. By the way, because of the unusual nature of this injection experiment in Los Angeles, the permit had to be signed by the cabinet of the United States government. The company, or Los Angeles, was given the company was given the permit for 2 wells. Only one has been built in Los Angeles County. So this is the world's first and still the only biosolids injection facility in the world. It's at Terminal Island. I've circled Terminal Island there with a bit of a ellipse, and it looks like this in August 2008, and it still looks like this. It's very clean, inobtrusive, etc. Well, what you've done by doing your waste treatment this way is that you've reduced your risks substantially, because now you've eliminated a substantial amount of transport. For example, the transport of sludge from your waste station out into the boondocks to place it. In Vancouver, sludge from the waste treatment is trucked 4 hours, 3 hours into the interior to be spread on forest land, because the market gardeners that grow your strawberries in the Lower Mainland do not want biosolid sludge spread on their farmland. India, again, going back to India, because India has a particular need for this type of waste disposal and carbon sequestration and getting rid of biosolids. And I've just outlined there the sedimentary basins that are suitable. Well, it turns out that the bright yellow one, which is called the Ganga River Basin, is home to about 500 million people. and has ideal geological conditions for this type of process. In cross-section, you've got a great thickness of sediments of high porosity and high permeability. This wedge lies from south of the Ganga River all the way into the, what do we call the Shiwalik rocks in the Himalaya. So it's a very thick wedge of essentially unlimited waste disposal capacity. And by the way, when we talk about biosolids waste, the process of decomposition at depth actually is a waste treatment process. So people that talk to me, they say, don't say waste disposal, Marie, say waste treatment. Okay, it's waste treatment, right. But we can also use it for other wastes, as I'll mention in a moment. Also, coastal cities like Chennai and Kolkata are suitable sites because they have, generally speaking, on the flanks of India, a sedimentary wedge that goes out to the sea with ideal groundwater conditions, because in a sedimentary wedge, you place your waste at depth, but the general groundwater flow is down and to the sea. Remember that when we talk about the Fukushima nuclear plant in a moment. And even better, you don't have to limit this to biosolids. Any organic waste can be ground and added to the biosolids. For example, there are people from the food industry here, and I know from experience that getting rid of milk whey, for which there is not necessarily a full market, turns out to be a very difficult process with a very large dairy industry, for example, in Oregon and California. So any organic waste can be added. Some amounts of non-hazardous, non-organic waste can be disposed of without any damage or any danger. It doesn't inhibit any of the bacteriological processes whatsoever, and the material is permanently sequestered at depth. For example, some non-recyclable plastics that otherwise have to be placed in a surface landfill, put into some kind of a high-temperature reactor, or disposed of by some other method. So that is co-disposal potentialities. Low surface footprint, you saw the surface footprint of a site, etc. And by the way, this could reduce the costs per ton of solid, dry biosolids treatment and disposal for the city of Los Angeles by about $35 a ton. Their costs are currently about $110 a ton for dry biosolids, and this should reduce that to on the order of $85, $75 a ton, depending upon a number of factors. And I put the website down here where you can visit the website for Terra and find out some more information maybe. So what is Terra doing right now? Well, Terra is a small company, Calgary-based, with operations in the Middle East, Indonesia, and it is oil industry based, so that it has followed the economic cycles of the oil industry. And the first thing, I assure you, that any oil company does when the oil price drops is they find some excuse to cancel their waste disposal project. Okay, that's invariably what they do. So the economic cycling in the oil industry has been a very big challenge for Terra. So last week, my ex-student and the president of the company was in Tokyo talking to TEPCO, Tokyo Electrical Power Company, about Fukushima and why. This is why. Every single item that those people are wearing will be thrown into a low and intermediate grade radioactive waste disposal container. And the number of these containers is multiplying daily. It's just increasing. They have a huge unresolved issue. Now, Fukushima sits right on one of those sedimentary wedges that thicken to the sea, and the groundwater is all flowing down into the sea. At 500 to 800 meters depth, and I've done the geology, the conditions are actually ideal. Now, low and intermediate level radioactive wastes are quite different from the high level wastes. Problem is that there's usually about 100 times the volume. They do not have a solution except ocean dumping. Every time you talk to TEPCO, you say, well, I've got this new technology, and they say, can we dump it in the ocean? well, actually, let's do this. We'd rather dump it in the ocean. So they're very, very blinded right now. So we're talking to them and seeing if this might be an alternative and, of course, much safer. Kuwait is a project that I hope in the next 2-3 months that the final contract will be written. A single source contract has already been drafted and partially signed. Why? This dates back to the invasion of Kuwait by Saddam Hussein a long time ago. And as he left, as his troops left, they opened up the oil wells and lit them on fire, which has resulted in all kinds of oil lakes, contaminated soil, etc. The Kuwaiti government was allocated, I think, an $8 billion or $5 billion reparations from the country of Iraq, and that chest of money, if you remember, was built up by the United Nations taking over the oil marketing of Iraq and giving Iraq people, or Iraq government, some of the oil money, but putting the others into the bank for reparations. Well, this is a huge amount of money, of which $250 million has already been totally wasted on technologies that just simply don't work, or technologies that cannot work economically at this scale. So I hope that I'll be very lucky if I'll be very proud if we can announce in the next few months that a contract for the first deep disposal site of oil field waste in Kuwait is handling the oil lakes, okay? These are not the best places to go bathing in the sand, sunbathing in the sand. They're kind of ugly and very challenging to deal with. The third project that Terra is trying to gain some traction in, and this is very, very difficult, is in oil sands sludges. At the bottom of these ponds are hundreds of thousands, perhaps now millions of cubic meters of an intractable sludge. And by intractable, I mean that there have been hundreds of patents, hundreds of millions of dollars spent on research as to how to handle that sludge, and so far there is no solution for some reasons that I could explain to you. This is an example of the tailings ponds that exist up in the oil sands mining area. And this is the intractable sludge. It actually is only a very small fraction of the overall tailings and wastewater, but it just stays the consistency of chocolate pudding no matter what you do. So we're doing site investigation and on a very tentative basis right now to look at the possibility of creating injection sites where this sludge would be placed 400 or 500 meters underground, where it then would be compacted and compressed by the weight of the earth above it. And this sludge just contains oil and clay and water. Although it's not pleasant, it is of itself not toxic. So putting it into an environment like that does not present a long-term risk. However, these are very radically new ideas to most of the companies, and sometimes it's a little bit challenging to get them to listen, especially when they're fighting off the barbarian hordes. And that's the problem in TEPCO in Fukushima, and that's the problem in the oil sands area with a low price. But at least the country of Kuwait and the companies in Kuwait have allowed us to move forward on this. And like I said, I hope that in the next few months we'll be able to make a major announcement about a long-term project in Kuwait. Thank you.